So the nth harmonic of a classical Fourier series is Hn given by an cosine n pi x over L plus Bn sine n pi x over L. So that's just exactly the summand that appears in the series, right? And so the use of this term harmonic refers to vibrations of strings, and this is why the study of Fourier analysis is sometimes also called harmonic analysis. So the frequency spectrum of a Fourier series, classical Fourier series, is the sequence of gammas, where gamma 0 is a0 over 2, and for the other values of gamma, it's given by an squared plus bn squared square rooted. And so this is exactly the amplitude of the nth harmonic. In order to see that, it's helpful to draw a little figure that involves a triangle and a change of coordinates. So here's our triangle. If I introduce some angle alpha, and here on the hypotenuse, this will be gamma, then we're going to have gamma cosine alpha on this side and gamma sine alpha on the other side. And then if we look at the nth harmonic here, so that we're going to have gamma n cosine alpha cosine n pi x over L plus gamma n sine alpha sine n pi x over L. And so here, these two guys, so this first one here, this is my an coefficient, and this one here is my bn coefficient, but I'm just rewriting it in terms of this new variable alpha, because then I have things in the form of a trig identity, which simplifies to being just cosine of the difference, so n pi x over L minus alpha. And so this whole thing now, you can see the amplitude of this superposition of sine and cosine n pi x L over L. The amplitude is given by this one here, right? So that's our the terms of our frequency spectrum. And then we have this phase angle here, which is our shift or offset. So we might have a cosine function that looks like, one period looks something like that. And so then what's going on here is we've got some amount of phase angle shift right here. That's the distance alpha that we're talking about. Anyways, so it's common to plot the frequency spectrum, so you can take a look at it and see where the big contributions are, what terms are really contributing to, or what frequencies are really contributing to your signal. And we also talk about the energy spectrum. And the energy spectrum of the signal is the sequence formed by squaring the frequency spectrum. And so the frequencies actually appear as eigenvalues of the Laplacian. And so that's why it's called spectrum, because we use the word spectrum to describe sets of eigenvalues. And energy spectrum comes up when you're looking at understanding those eigenvalues as energy states. So in this form, the Parsifal identity takes the form 1 over L magnitude of f squared is equal to a0 over 2, a0 squared over 2 plus the sum of, and we have the an squared plus bn squared. And so again, you can see that's a version of Pythagoras' theorem.